own safety. These coded hand signals can be broken down into 4 categories. These are general signals, signals for vertical movements, signals for horizontal movements, and danger signals. The figures that will follow will provide valuable insights into each type. In the first figure, we can see an operator with both arms extended horizontally with the palms facing forwards. This notifies the start of the operation. In this next figure, the right arm of the operator points upwards with the palm facing forwards. This indicates the end of movement or a stop. Here, both hands are clasped at chest height. This indicates the end of the operation. In this example, the operator's right arm points upwards with the palm facing forward and slowly makes a circle. This indicates a vertical upward movement or a raise signal. When the right arm points downwards with the palm facing inwards and slowly makes a circle, it indicates a vertical downward movement or a lower signal. This next figure is for vertical distances. Here, the hands indicate the relevant distance. Now, for horizontal movements, when both arms are bent with the palms facing upwards and the forearms make slow movements towards the body as depicted here, then this indicates a move forwards signal. When both arms are bent with the palms facing downwards as seen here, and the forearms make slow movements away from the body, then this indicates a move backwards signal. The next hand signal is self-explanatory. When the right arm is extended more or less horizontally with the palm facing downwards and slowly makes small movements to the right, it indicates a horizontal movement on the right side, as opposed to this hand signal indicating a horizontal movement on the left side. This next figure is for horizontal distances. Here, the hands indicate the relevant distance. Finally, a dangerous situation can be indicated by the following hand signal. In this situation, an emergency stop is required. The next couple of videos aim to provide and share good practices for lifting operations. The pictures that will follow will be accompanied by either a green tick or a red cross. A green tick, as depicted here, shows the correct practice. A red cross, on the other hand, shows the wrong practice. Please feel free to share these good practices with your colleagues to enhance safety at your workplace. The key safe points that will be covered next include general safety operation for cranes, mobile cranes, outriggers of cranes, tower cranes, test and examination of lifting gears, safe working load, lifting gear before and after use, maintenance of rope wire slings and chain slings, shackle, hooks, focus area for using different types of lifting gears, rigging methods, lifting plans, safe lifting, surrounding conditions, and weather conditions. In the next couple of videos, we will examine each one of them in detail. As a first and basic safety rule, do not lift any load with weight exceeding the safe working load. Now, although this seems quite basic and logic, it remains one of the most critical aspects of lifting operation and may lead to catastrophic failure. When the crane is in operation, avoid abruptly swinging or stopping the crane. As shown now on screen, this may result in loss of balance and control of the load. In case of adjacent building or structure, this may result in serious damage. A good practice is to never move the load at high speed and use low speed when approaching to destination. The next safety rule is to never drag the loads on the ground, as highlighted here. The following picture shows one of the most common unsafe behavior during lifting operation. Please keep in mind here, never pass below a load. To avoid having unauthorized entries in the lifting zone, lifting routes should never be overlooked. They should and must be detailed, carefully examined, and safely planned. Mobile cranes, as in this example, should be operated on a firm and level ground that could adequately support the weight of the crane and its loads. Mobile cranes should travel on flat and firm ground to prevent overturning of crane. In addition, the boom length of the crane should be adjusted to ensure the mobile crane is operated within the extent of the safe working radius. Now, when mobile cranes must travel on a slope, as depicted here, a sufficient buffer should be allowed for the lifting load. The working radius should be reduced to prevent topple of crane and overload. In addition, spin lock and swing brake should be applied, and the lifting loads should be as close to the ground as possible. When operating a mobile crane, the crane operation area should be fenced off. A minimum clearance of at least 1 meter should be maintained between the mobile crane and the walkway. The counterweight of the crane should be painted distinctively, usually striped yellow and black as in this example, and a notice in English or in the local language should be displayed on the crane and on the fences, stating that no person is allowed to access to any part of the crane without permission. Take a look at the following figure. It shows the correct positioning of crane outriggers. Crane outrigger pads should be at least 3 times larger than the area of the float. Steel plates, as seen here, of adequate strength, suitable pad or timber block should be used. Cylinders should be perpendicular to the float, as seen here, and the recommendation and instruction of the manufacturer should be followed to ensure the stability of the crane. Of course, the proper setup of outriggers should be checked before lifting operation. The following figure depicts incorrect positioning of crane outriggers. This unsafe setup should and must be avoided. In this situation, the crane is unstable. The lifting operation will be unsafe. And if you allow lifting to proceed, catastrophic outcomes will be the result, with potential fatalities, serious injuries, and certainly extensive damage to the properties and to the facility. Tower cranes are a very special type of cranes. They are widely used in construction sites. The following picture depicts a typical example of a tower crane. Now, unless there are heavy construction activities at your facility, you won't be involved with tower cranes. However, here are a couple of good and safe practices. First, when the tower crane is not in operation, the trolley of the crane must be positioned near the tower at minimum radius, with the hook raised to its highest position, as highlighted in this example. Now, if 2 or more tower cranes are operated in a construction site with overlapping zones, as is the case here, do not forget to provide an anti-collision system for the cranes to prevent collision within the overlapping zones. The functional system testing should be conducted regularly, at least once a week. The anti-collision system should transmit a continuous audio and visual signal to the cabin of the tower crane. This system reminds the crane operator to slow down the crane when the crane approaches a zone with the risk of collision. The lifting gear should be tested and thoroughly examined by a competent examiner before use in the first time, and then thoroughly examined every 6 months. The purpose is to ensure that the lifting gears are in good condition. As a good industry practice, the color code system can assist you to identify whether the certificate for the lifting gears has expired or not. When a lifting gears has passed the quarterly examination with a valid certificate, it should be sprayed with the designated color of the quarter. For example, a lifting gear passing the examination in, let's say, June, should be sprayed with yellow. The safe working load, referred to as SWL, is the highest load that the lifting gear can lift under certain conditions. Keep in mind here, and always remember, the work should be performed under safe working loads in all situations. The safe working load and identity number of all lifting gears must be displayed clearly and easily visible to all workers. In this example, the safe working load is 5 tons, roughly 11,000 pounds, and the identity number is as follows. Okay, Now, always ensure that the lifting gear is in good condition before use. And then, after use, the lifting gear must be placed in the designated place and properly stored, as highlighted in this example. Take a look at the following figure. It depicts unsafe and unusable rope wire slings, damaged wires, wires with burnt gauges, wires with worn surfaces, and wires with changing diameter should never be used under any circumstances. The next figure depicts unsafe and unusable chain slings. Stretched, bent, cracked, or worn chain slings should never be used under any circumstances. Take a look at the following figure. It depicts a typical example of a lifting shackle. The lifting shackle is one of the steel lifting accessories. It can be straight, as in this example, lyre, screwed, or bolted, depending on the use. When a lifting shackle is used, it should be used as highlighted here. If the lifting shackle is positioned the other way around, as seen here, and if the load shifts, the sling will unscrew the shackle pin and the load will fall, with the potential to cause serious damage. In addition, keep in mind never replace the shackle pin with a bolt under any circumstances, and always ensure that the pin is totally locked. When using hooks, always select hooks with the right size. Never tie or remove the safety latch, and maintain the hook in the vertical position. Keep in mind if the hook is eccentrically loaded, the safe working load will be reduced. Recall, the safe working load is the maximum load that the lifting gear can lift under certain conditions. Okay, now when lifting material with a non-symmetrical center of gravity, as in this example, you should conduct an evaluation before the lifting operation. The center of gravity of the load should be checked and applied during lifting to ensure balance. In this example, balance is ensured by using lifting slings of different lengths. In addition, for optimum safety, feel free to use specific lifting tools for lifting different objects. In this example, lifting clamps are used to lift an I-beam. Loose loads, as in this case, should be packed and placed in suitable containers before lifting. The containers must be structurally sound, tested, and examined by a competent worker. And then suitable slings must be used for lifting to avoid container tilting. Corner pads should be used for loads with sharp edges, as in this example. It is important to keep in mind here that fiber slings are not suitable for use in this type of lifting operation. Fiber slings are only used for lifting tubular and easy-to-wear objects, for example, materials with round shape and without sharp edges. Lastly, when lifting large or heavy loads, as in this example, wind factor, working location of the crews, and operator's visibility must be considered. Let's now discuss the best practices for rigging methods. As seen from the following figure, if two or more lifting slings are used, their upper ends should be connected by a shackle of an adequate strength. Every part of the load should be balanced and securely fastened to prevent slipping or displacement of any loose objects during lifting. For example, and as seen here, double wrapping, straps, and tag lines should be used for lifting materials such as steel bars in order to secure and stabilize the rigging. The following picture illustrates the use of a lifting tag line. Here, the tag line is used to maneuver the suspended load and keep it from rotating and swinging. In these situations, it is important to keep in mind that nearby workers should be kept at a safe distance, and that the tag line should never be entangled. Otherwise, the load will be destabilized, it may rotate and swing, causing a hazardous situation. The lifting plan provides a systematic approach towards planning a lift and ensures that the lifting operation is properly managed. For example, a lifting plan would ensure that the crane is safely deployed and operated, and the lifting crew are clear about their roles and responsibilities. Detailed lifting plan and method statement should be prepared and clearly delivered to all frontline staff prior to every lifting operation. The lifting plan should include, at a minimum, the following elements: details of the load, lifting equipment and gears, lifting crew, including their roles and competencies, the lifting method, the requirements to erect or dismantle the lifting equipment if applicable, the means of communications, a sketch of the lifting zone showing position of lifting equipment, crew, and load, and any other important information such as special precautions. Once the lifting plan has been established and approved, you should never deviate or vary from the approved version. So keep in mind, if the actual information at the lifting site does not comply with the lifting plan, you should stop the operation until the plan has been updated and reapproved. Now, the following information should be acknowledged to conduct a risk assessment before the implementation of the lifting plan. These include the jib length, referred to here with the letter A, the lifting radius, B, the weight of the hook, C, and the weight of the load, D. From our experience, we have witnessed many deviations from the good practices highlighted so far. We have also seen some special lifting operations which we do not recommend unless there is no other option. These special lifting operations include tandem lifting, as highlighted here, and using excavator for lifting purposes. These are high-risk lifting operations, and as we said, should be avoided as far as practicable. However, if the lifting operation is unavoidable, a detailed plan should be made and approved by competent persons before the operation. In addition, for these special lifting operations, we strongly recommend the use of a walkie-talkie for communication instead of the hand signals. The objective here is to avoid confusion or misinterpretation. In addition, only one signaler is allowed to give signal, and if the communication fails or the signal is unclear, the lifting operation must be stopped immediately. Okay, now in addition to all what we have discussed so far, keep in mind the following safety rule. This lifting rule is called 3-3-3 and is symbolically depicted as follows. So keep 3 meters away from the load being lifted. Then lift up the load 300 millimeters from ground. Then wait for 3 seconds to stabilize the load before resuming the lifting operation. And don't forget that the lifting zone should be properly fenced off with barriers, as seen here. Prominent notices should be provided to prevent unauthorized persons to enter into the lifting zone. Okay, now always remember that the lifting route should be properly planned to ensure no collision with any person, object, or overhead power lines as depicted in this example. Overhead power lines should be stayed clear from the working location. The safety distance must be at least 9 meters away from the length of the jib. When the lifting is carried out adjacent to a slope edge, as in this example, the operation should be kept at a safe distance from the slope edge. Keep in mind here, for your own safety, that when the operation is close to the edge of a soil slope or an unsupported soil excavation, the soil may collapse. This will cause the toppling of the crane, as the load-bearing capacity is much lower than those away from the edge. So please always check with a competent person if in doubt. The inspection of the ground conditions before work should include, at a minimum, the following items. First, the ground should be thoroughly checked to ensure that it has enough load-bearing capacity at the working location to support the crane and its load. And second, precaution should be taken to ensure that the potential crane standing location is clear of any underground services. Otherwise, the services should be adequately protected to safeguard against any damage. The picture shown on screen provides guidelines regarding the various distances. For example, for safe and stable lifting, the crane should be located at a distance away from the slope greater than 4 times the width of the foundation. When the wind speed exceeds the limit set by the crane manufacturer, the crane operation must be stopped. The jib of the crane should be lowered down and placed such that it will not be affected by strong winds. If possible, we recommend the use of strong supports so that the jib can rest on them. Heavy rains may cause slippery ground, low visibility, loose soil, and landslides. Whenever the following conditions happen, lifting operation should be stopped. Soil condition is loosened and affects the stability of the crane. Or low visibility is affecting the vision of the crane operator or the signaler. Or the weather observatory of your location hoists black rainstorm warning signal. Whenever any of these conditions happen, lifting operation should be stopped. Thunderstorms may have a certain impact on the lifting operation. It is difficult at this stage to provide a clear safety guideline. However, having said that, in case of thunderstorms, we advise you to consult your management, your emergency preparedness plan, and the actual condition to decide to suspend the lifting operation or not. We truly hope that this video provided good practices for lifting operations that will enable you to enhance safety at your workplace. Please feel free to share these good practices with your colleagues and let us know if you need further details. You can drop us an email on contact@wrtraining.org or ask us for help in the Q&A section. Thank you for watching.
In January 2018, a truck driver was seriously injured when he was struck by a suspended load during the unloading of equipment at a worksite. The other workers involved in the unloading operation, including the site's supervisor, dogman, and crane operator, all received a pre-start briefing about loading and unloading at various locations across the site, held relevant high-risk work licenses, and wore full PPE. The truck driver, who arrived later, was not involved in the briefing, and was not fully inducted onto the site by the principal contractor. He had completed one delivery to the site on the day of the incident, and was escorted to a second location where an item of piling plant was unloaded from the truck. 6 steel pile casings, 5.7 meters in length by 1 meter in diameter, and weighing approximately 4 tons, were then loaded by mobile slewing crane onto the trailer of the truck. The steel pile casings are tubular-like pipes used to form the piles. These were secured and transported to another location on site for unloading by crane. The rigging method used to unload the casings was the handshake method. The handshake method requires the crane operator to place the crane's boom and hook over the center of the casing. The chain sling is then lowered to the casing, and one chain leg threaded through the casing's inner circumference, latching its hook to the hook of the second chain, like a handshake. The connected hooks were positioned in the center of the load. A rope tagline was tied to a chain leg to allow the dogman to manually control the load's lateral movement during lifting. The first 2 loads were lifted and landed without incident, although the truck driver stood on the trailer throughout the lifting operation. While the site supervisor was directly involved in the first lift, he moved some distance away prior to the second lift and was not directly supervising the operation. The dogman and the truck driver set up the third lift. The truck driver, who did not hold a high-risk work license for performing dogging work, remained standing on the bed of the trailer and signaled the crane operator to commence the lift. As the casing was lifted slightly above the trailer's bed, the action of lifting the load before the boom was positioned over the casing's center of gravity, and before the rigging was properly centered within the casing, caused the load to shift sideways as it was lifted. The truck driver was struck with the end of the casing, trapping him between the suspended load and another casing on the truck. He sustained serious crush injuries, requiring hospitalization. An investigation into the incident identified that the piling company failed to enforce a safe work procedure for loading and unloading objects from trucks, including enforcement of an adequate exclusion zone around trucks during unloading operations, enforcing a requirement that non-essential personnel, such as the truck driver, remained outside of the exclusion zone at all times. Ensure workers are adequately supervised, and only those workers who hold the relevant high-risk work license undertake high-risk work. Before high-risk construction work commences, ensure that a safe work method statement for the proposed work is prepared, and the work is carried out in accordance with the safe work method statement. A person must not carry out a class of high-risk work unless the person holds a high-risk work license for that work. Only an allocated dogman is to signal a lift to a crane operator once the correct crane hook positioning is confirmed. When lifting with cranes, an exclusion zone is to be in place to prevent crush injuries to workers from potential uncontrolled movement of loads. Workers should be adequately supervised to ensure that non-essential workers remain outside of the exclusion zone at all times.
focuses on hazardous substances in refineries and chemical plants. Now, as well as all hydrocarbons, nitrogen, hydrogen sulfide, hydrogen fluoride, and many other hazardous chemicals are handled routinely in refineries and chemical plants. Contact with these can prove fatal in a matter of seconds. This section was created to help share knowledge and improve the understanding on the basic principles for the safe handling of the main hazardous chemical products found in refineries and chemical plants. We strongly recommend you take the time to watch this section carefully. Please note here that the usefulness of this section is not limited to operating people. There are many useful applications for the maintenance, design, and construction of facilities. Please feel free to share your experience with others, since we believe this is one of the most effective means of communicating lessons learned and avoiding incidents in the future. To begin our discussion, let's first answer a basic question. What are hazardous substances? Hazardous substances are any material or item that has the potential to harm humans, animals, or the environment. They can act directly or through interaction with other factors. Petroleum and chemical facilities in particular handle large amounts of highly hazardous substances. These materials are most dangerous when released uncontrollably. So it is important that you recognize the threat and know what steps to take when exposure is likely. The following are some of the most frequently encountered hazardous substances in the petroleum and chemical industries. Does your site handle these materials? Can you identify the hazards they pose? Please go to the next videos to find out more. To begin our discussion, let's first emphasize the following two important points. First, the data found in this section should not be used as a replacement for your site's material safety data sheets. Second, the information contained in this section is only provided to raise awareness. It may require you to do additional research if you are likely to encounter hazardous materials in the course of your work activities. Now, in view of the dangers of handling hazardous materials, several international bodies have classified them according to the threats they pose. Some of these bodies are now shown on screen. In general, and as already discussed, hazardous materials can be categorized as follows: toxic, corrosive, flammable, explosive, radioactive, cryogenic, and reactive. Some substances can be a combination of these categories. For example, benzene is both flammable and toxic. In this regard, we can share the following accident that occurred in a chemical plant where benzene was treated in a benzene splitter. As seen here, the operator was opening a manual gate valve as part of the startup procedure, when suddenly benzene started leaking and spraying from the valve due to packing failure. The spray of benzene hit the operator in the face and body, and although the operator was given emergency treatment, he did not survive. Now, it is important to keep in mind here that the physical form of a substance sometimes determines its potential risk. A substance that is safe in its solid form may be toxic or flammable in its vapor state, or give off hazardous fumes in its liquid form. In addition, we are most often concerned with materials that give rise to immediate consequences, but hazardous substances also constitute materials that only display adverse consequences many years later. For instance, asbestos can cause asbestosis, a scarring of the lungs that leads to breathing problems and lung failure. Workers exposed to asbestos for a short time may develop lung cancer, which only becomes evident 20 to 30 years later. Substances that are toxic can trigger adverse health effects in the human body. The severity of these effects depends upon the toxicity of the material, as well as the amount involved. This amount is often referred to as the toxic dose. In a later video, we will detail the routes of entry of toxic materials into the body, and then define some important toxicology concepts. Here, it is important to know the acute effects, as well as the chronic effects of toxic substances. Now, we cannot talk about toxic chemicals without saying a word about the Bhopal disaster. a plant in Bhopal, India, produced pesticides using methyl isocyanate, more commonly known as MIC. In this process, MIC was used as an intermediate compound. MIC is an extremely dangerous compound that severely irritates the nose and throat, causing respiratory distress. On the day of the accident, on the 3rd of December 1984, an estimated 25 tons of MIC vapor was released. The toxic cloud spread over a shanty town nearby, killing 2,000 and injuring a further 20,000, marking it as one of the most significant disasters in the history of the chemical industry. Now, briefly, the Bhopal plant was storing MIC in 3 separate tanks, as seen here, E610, E611, and E619. These tanks were connected to a vent gas scrubber, as seen here, a cooling system, and a flare. The vent gas scrubber was designed to detoxify any leaking MIC vapor. The cooling system was used to cool MIC and prevent liquid evaporation to form toxic vapors. The flare system, on the other hand, was designed to burn off any MIC vapors. On the day of the accident, the scrubber was turned off. The cooling system was shut down to save on operating costs, and a connecting pipe on the flare system was removed for maintenance. So the flare system was unavailable. The tank E610 contained 40 tons of MIC, E611 15 tons, and the tank E619 was empty. Water entered tank E610, causing a runaway heat-producing reaction. This resulted in an overpressure within the tank that subsequently caused a release of MIC, as seen here. As a result, the toxic cloud spread over the town, killing 2,000 and injuring a further 20,000. Now, the photos that will follow next were taken days after the accident, and outlines once again that the Bhopal disaster is undoubtedly one of the most significant disasters in the history of the chemical industry. Now, some of you may find the following photos disturbing, so your discretion is advised. These photos were only provided to raise awareness that contact with hazardous chemicals can prove fatal in a matter of seconds. Now, there are many lessons to be learned from Bhopal, but the most important is that the material which leaked, so methyl isocyanate, MIC, need not have been there at all. It was an intermediate, not a product or raw material, and while it was convenient to store it, it was not essential to do so. Originally, MIC was important and had to be stored, but later it was manufactured on site. The main lesson of Bhopal is what you don't have can't leak. Thus, whenever possible, you should reduce or eliminate inventories of hazardous materials in process or in storage. This is at the heart of the inherently safer design philosophy. So, do not overestimate your ability to keep hazardous materials under control. If you do that, you will not look for ways of reducing inventories. Yet, to keep hazardous materials under control, you will need expensive added-on protective equipment, safeguards, and safety instrumented systems, which may fail or may be neglected. Intermediate storage is usually wanted by plant managers as it makes operation easier. One section of the plant can operate when another is shut down. In addition, engineering studies on equipment availability always show that intermediate storage is needed. However, they do not allow for the fact that if intermediate storage is available, it will always be used, and maintenance will be carried out at leisure. But if intermediate storage is not available, people do everything possible to keep the plant online, carrying out maintenance as soon as possible. So the need for intermediate storage is a self-fulfilling prophecy. Corrosive materials are substances that can cause visible damage or irreversible alterations to living tissue. They can act directly by chemically destroying the tissues, or indirectly through inflammation. These injuries are sometimes referred to as chemical burns. Acids and bases are common corrosive materials. Typical examples are hydrofluoric acid, hydrochloric acid, sulfuric acid, and sodium hydroxide. Corrosives such as these are sometimes referred to as caustics. The severity of damage to living tissue following contact depends largely on the type of substance, the concentration of corrosive material, and the contact area. In the case of hydrofluoric acid, the acid continues to attack the calcium in bones and is a particularly insidious chemical, requiring special precautions to avoid exposure and to treat properly. The following animation provides insights into the threat posed by hydrofluoric acid as it penetrates the human body.
HF can penetrate skin because it's miscible with both water and fat. The hydrogen-fluorine bond is so strong that the molecule stays intact until it reaches deep tissue. There, it dissociates, producing hydrogen ions, also known as acid, and highly reactive free fluoride ions. These fluoride ions wreak havoc on tissues, turning them into viscous goo. They also bind with calcium and other positively charged ions. That causes your nerves to release potassium ions, which you feel as horrible pain.
Flammable materials are substances that can catch fire. Fires are obviously dangerous because they can cause burn injuries to the human body, widespread acid damage, and release of toxic fumes and pollutants into the atmosphere. Combustible materials also have the potential to burn, but require higher temperatures to pose a significant risk. However, even combustible materials can ignite at lower temperatures if they exist as a mist. Thermal burns are a result of exposure to thermal energy radiated from fires, as depicted here. The intensity of the thermal radiation emitted in a fire depends on the type of flammable material, the amount of flammable material, the pressure of release, and the surrounding conditions. All of these factors will be discussed in detail in a later video. But regardless of these items, 3 elements must be present before a fire can happen. These are fuel, oxygen, and an ignition source. The absence of any one of these elements means that a fire will not occur. Examples of oxidizers are air, oxygen, and fluorine for gases, hydrogen peroxide for liquids, and metal peroxides for solids. Examples of ignition sources include sparks, flames, static electricity, and heat. Examples of fuel are acetylene and propane for gases, gasoline and acetone for liquids, wood dust and plastics for solids. Keep in mind here, vapors and liquids are in general easier to ignite. Now, it is often best to eliminate the oxidizer to prevent fires from occurring, rather than the ignition source, because ignition sources, even if identifiable, are always difficult to control. So please keep this in mind. If you want to prevent a fire from occurring, the best thing to do is to eliminate the oxidizer. In almost all practical cases, this means eliminate ingress of air or oxygen into your process. Keep in mind here, the combustion always occurs in the vapor phase. Liquids are volatilized and solids are decomposed into vapor before combustion. In addition, for an ignition to occur, the fuel and air or oxygen mixture must be within a certain range. This range is determined by the lower flammability limit or lower explosive limit and upper flammability limit or explosive flammability limit. Note here that the lower explosive limit LEL and the upper explosive limit UEL are used interchangeably with LFL and UFL. Now, different flammable materials will have different flammability limits. For example, benzene will have a lower flammability limit of 1.2% and an upper flammability limit of 5%. Methane, on the other hand, will have a lower flammability limit of 5% and an upper flammability limit of 15%. And here the range for kerosene. Okay, let's now take a closer look at benzene. The figure that you see now on screen represents the flammability range of benzene in air at ambient temperature and atmospheric pressure. It is important to keep in mind here that benzene vapor-air mixture will ignite and burn only over a well-specified range of compositions. In this case, when the mixture contains between 1.2 and 7.8 benzene. The units are volume percent fuel, so percentage of benzene in benzene air mixture. The mixture will not burn when the composition is lower than the lower flammability limit. When the composition is lower than the lower flammability limit, the benzene air mixture is too lean for combustion. The mixture is also not combustible when the composition is too rich, that is, when it is above the upper flammability limit. Keep in mind a mixture is flammable only when the composition is between the LFL and the UFL. Notice that in this example, we have talked about the flammability of a pure component at ambient temperature and atmospheric pressure when mixed with air. In a later video, we will discuss flammability of mixtures, flammability of components when mixed with pure oxygen or other oxidizers, as well as flammability of mixtures at temperature and pressure other than standard conditions. These topics are important because they are at the heart of conducting safe operations, in particular during equipment inerting, purging, plant startups, and shutdowns. A pyrophoric is any material that will spontaneously ignite and burn when exposed to air. A typical example of a pyrophoric substance is triethyl aluminum. Triethyl aluminum, more commonly known as TEAL, is a routinely used co-catalyst in various petrochemical processes. Now, what might happen if a bottle of this pyrophoric liquid were to drop and break? I think that pretty much speaks for itself. The next video provides additional insights into the hazardous behavior of triethyl aluminum when exposed to air or when mixed with water. The safety message here: never underestimate the destructive potential of these materials. You must maintain a healthy respect at all times. Explosive substances are compounds that can undergo rapid chemical reaction, decomposition, or combustion to generate large amounts of heat and gases. A typical example is trinitrotoluene, more commonly known as TNT. The generated gases have a combined volume much greater than the original substance, which produces a rapidly moving pressure or shock wave, as seen here. It is the shock wave that causes explosion or blast damage. Explosive vapors in air can ignite if the mixture is within the explosive or flammability limits. On the other hand, some explosives do not need to be in an oxygen atmosphere to detonate, as the oxygen is chemically bonded to the explosive compound, and thus the oxidizer is readily available. Some materials are shock sensitive and can explode by friction or touch, while other explosions can be caused by mixing incompatible chemicals. This is common in laboratory accidents. Now, you're watching this video presumably because your job does or could bring you in contact with some of these materials. Perhaps it will be under normal or non-hazardous circumstances, or perhaps it will be in response to some emergencies. In either case, what you don't know just might kill you. Now, it is not our intention in this video to show you how to properly store or handle or neutralize these materials. This will be dealt with in a later section. In this video, it is our intention, however, to demonstrate just what some of these relatively common materials are capable of doing. Materials that are routinely used in refineries and chemical plants. Nitroglycerin is a typical example of an explosive compound. It is a relatively stable product and will therefore withstand normal storage and handling safely, and requires a fairly high degree of heat or shock to detonate. Under normal conditions, it behaves very predictably. All things considered, it is a reasonably safe product. When detonated, it releases a high degree of energy. Let's take a closer look. In this demonstration lab, about 1 ounce of nitroglycerin is placed on a stand, and an electric blasting cup was inserted into it to initiate it. Watch the bottles in the proximity. That was a detonation. A detonation is the extremely rapid and violent decomposition of the material, producing a shock wave which may be extremely destructive to nearby objects. As a direct result of such a detonation, a high-pressure shock wave radiates outwards in all directions. It is this shock wave, with its accompanying overpressure, that causes much of the damage. Here is, for illustration purposes, the destructive overpressure of 1 pound of an explosive compound. 10 feet from the explosion, the overpressure would be 5 pounds per square inch. Now, that's 5 pounds over normal air pressure. It is enough to kill you. At 16 feet, the overpressure has dropped to about 3 pounds, enough to do serious damage to structures and buildings. At 40 feet, about 1 pound, enough to break windows. At 250 feet, the pressure, about now 1/10 of a pound, is still enough to break some windows. Now, the power of an explosion does not only depend on the amount and type of substance involved, but also on the degree of confinement and obstacle density. This will be discussed in detail in a later session. But for now, keep in mind that, in general, areas of higher degrees of confinement and obstacle density produce more severe blasts. In addition, large explosions are extremely dangerous because they often cause structural damage, which can result in collapse or damage to equipment or piping system, which adds to the severity of the situation and can result in further loss of life. One of the main dangers in an explosion is the severe hazard caused by flying debris or from collapsing structures. Radioactive materials are substances that can emit energy spontaneously. The energy, referred to as radiation, is produced when changes occur within the nuclei of atoms, as seen here. Exposure to radiation can affect the body in a number of ways. Exposure to very large doses of radiation may cause death within a few days or months, while exposure to lower doses may lead to skin reddening and an increased risk of developing cancer or other adverse health effects. The adverse health consequences may not be observed for many years. Now, the best way to protect against exposure to radiation is to avoid these materials altogether in the first place. However, if this is not possible, then limit the amount of time spent near the source of radiation. Increase your distance from the source and make sure the appropriate forms of shielding or barrier are in place. In addition, a personal dosimeter can be worn to monitor the radiation dose absorbed. Okay, let me now provide a real example that occurred at our refinery and which illustrates how accident involving radioactive substances can occur. In this example, a radioactive material was disposed as scrap. A radioactive level gauge on a tank was to be replaced with a non-radioactive level measurement device. The person in charge instructed 2 craftsmen at our facility to remove the level gauge equipment entirely, thinking that the radioactive source has already been extracted. But this was not the case, as he had confused this tank with another tank, where the radioactive material had indeed been removed. A normal permit to work was used instead of the special form for handling radioactive equipment. As a result, the craftsmen removed the level gauge with the radioactive source still intact, and placed it in a scrap container for disposal. The container was only found to contain radioactive material when the disposal company performed a routine check for radiation at their site. The radioactive source holder was isolated in a dedicated containment and was traced back to our facility. Now, the cause of the incident was a failure to check the status of the level gauge and cross-check this with the responsible department for radiation protection. If the disposal company had not performed a check for radiation, the radioactive material would have been lost and left to contaminate its surroundings, or perhaps subject disposal site personnel to radiation exposure. Now, although the subject of signs and symbols was discussed in a previous session, here are some additional insights into the topic. Now, recall, systems of signs and symbols for hazardous substances have been developed by several agencies and organizations to provide quick identification and double up as warning signs for handlers. They are required to be placed in prominent locations and should be hardy enough to withstand the elements and damage. 2 examples of codes and signs for classification of hazardous materials are provided in this video. These are the National Fire Protection Agency Diamond and the International Maritime Dangerous Goods Code. The latter was discussed in a previous video. Please refer to the video in question in case you need to refresh your memory on these pictograms. The NFPA diamond is self-explanatory. It defines the safety square or fire diamond, which is used to quickly and easily identify the risks posed by hazardous materials. This helps determine what special equipment should be used, procedures followed, or precautions taken during the initial stages of an emergency response. It is an internationally accepted safety standard and is crucial while transporting chemicals. The 4 divisions are typically color-coded with red on top indicating flammability, blue on the left indicating level of health hazard, yellow on the right for chemical reactivity, and white on the bottom containing codes for special hazards. Each of health, flammability, and reactivity is rated on a scale from 0 to 4, 0 corresponding to no hazard and 4 corresponding to severe hazard. The latest version of NFPA diamond for the specifications of each classification are listed in the following tables. These tables are available for download in the Downloadable Resources section. For example, a flammable chemical rated 4, as seen here, corresponding to a severe hazard, will rapidly or completely vaporize at normal atmospheric pressure and temperature, or is readily dispersed in air and will burn readily. Examples of highly flammable substances include gasoline, propane, and hydrogen gas, just to name a few. This category also includes pyrophoric substances such as triethyl aluminum, for which the destructive potential was discussed in a previous video. When hazardous substances are used or handled, several issues must be considered. They include, among others, approval from the relevant authorities, adequate safe storage facilities, amount stored to be within safe limits, reliable release detection systems, appropriate mitigation measures and safeguards in the event of release, prominent signs, labels, and warnings, training for safe handling and emergency response, safe disposal, and substance details, and in particular, the safety data sheets. Before any of the steps highlighted here are taken, and before any of these hazardous materials are used, the following questions should be considered. Is this chemical really needed? Can it be replaced with a less hazardous substance? If the use of a hazardous material can be substituted with a safer material, the potential hazards that may arise can also be reduced. If a less hazardous material is selected, careful consideration must be given to make sure that no unforeseen problems arise from its use and that it can perform as required. On the other hand, when a hazardous material cannot be substituted, make sure that risk assessments and job safety analyses are performed. This should be done to identify the possible hazardous scenarios, determine the risks to personnel, determine if sufficient safeguards are in place, and identify what further safeguards may be required. In all cases, we strongly recommend to follow a proper management of change process when changes are made to chemicals being used. Safety data sheets contain useful information for the safe handling of hazardous materials. They are prepared to provide clear and concise information for quick reference. The information contained in safety data sheets is useful for day-to-day operations, but is vital during emergencies. Safety data sheets of all hazardous materials must be available at strategic locations for easy access by plant personnel, for example, in control room. They must also be provided to emergency response services to ensure that correct measures are taken in the event of an incident. Safety data sheets should contain, at a minimum, the following information: identification of the substance and of the company, composition of the substance or information on ingredients, hazards identification, critical hazards to man, such as symptoms and adverse health effects, first aid measures, including instructions for action on the spot and whether or not assistance by a doctor is needed, firefighting measures detailing suitable extinguishing media to be used, as well as extinguishing media that must not be used, combustion products or gases, and special PPE requirement for firefighters. In addition, reference should be made to accidental release measures for the focus on personal and environmental precautions and the adequate method for cleaning up. Handling and storage conditions should also be included in the safety data sheets. Some hazardous substances require to be stored below certain temperatures. This is the case of organic peroxides. Organic peroxides may be any liquid or solid organic compound that contains oxygen in its structure. A general chemical structure is now shown on screen. Here, the letter O refers to the oxygen atom, the letter R to a hydrocarbon group. What all this means is that it is both a fuel and an oxidizer. Nasty stuff. Such compounds release their oxygen readily and are capable of violent decomposition. A common hazard of organic peroxides is their tendency to decompose when they get too warm. Terms commonly used to describe this characteristic are SADT for self-accelerating decomposition temperature, or MSST for maximum safe storage temperature. The temperatures vary from material to material. Now, for the purpose of illustration, here is an organic peroxide with a self-accelerating decomposition temperature well below room temperature. This sample was removed from the refrigerator and it has reached its self-accelerating decomposition temperature. Observe how this material behaves under such conditions. Now, keep in mind here, some peroxide liquids simply off-gas vigorously, as in this example. Some off-gas and burst into flame, while others may explode quite violently. Okay, safety data sheets should also include exposure control and personal protection. For instance, the type of equipment for respiratory, hand, eye, and skin protection. Physical and chemical properties such as appearance, odor, pH, boiling point, melting point, flash point, O2 ignition temperature, and so on. Stability and reactivity with reference to conditions and materials to avoid, in particular reference to incompatible chemicals. Toxicological information detailing both immediate and delayed health effects. Ecological information such as mobility, degradability, accumulation, ecotoxicity, and any other adverse effects. In addition to disposal considerations, regulatory information, and transport information. Please note here that from our experience, transport information in safety data sheets are usually overlooked. This is, from our perspective, a big mistake. A typical example where overlooking transport information can lead to catastrophic consequences is when handling chemicals such as ammonium nitrate. Ammonium nitrate is a very common solid oxidizer. It may be used as a nitrate fertilizer and also as a blasting agent. In their original state, that is properly packaged and stored, these compounds are relatively safe. However, when the packaging is damaged, as could easily occur in transportation or storage accident, they can become contaminated. Should this occur, they could assume totally different and quite hazardous characteristics. In this demonstration lab, a few ounces of ammonium nitrate were contaminated with a common flammable liquid. The mixture was then initiated. Watch the bottles and the lab technician in the proximity. I think that pretty much speaks for itself. Never overlook safety information on your safety data sheets, and never underestimate the destructive potential of hazardous materials. Again, this is why safety data sheets are useful for safe day-to-day operations and vital during emergencies. The main safety message here: always ensure that you have continuous access to up-to-date safety data sheets for all the products at your facility, both for process and other activities such as maintenance, cleaning, and firefighting. To better illustrate the importance of this safety message, let me share with you an accident that occurred in a petrochemical plant where a confined space incident escalated due to confusion over properties of material. Here, two operators rushed to the scene when they were summoned to rescue their colleague who had fallen unconscious in a tank which still contained some toluene. The worker entered the tank to perform cleaning operations without proper protective clothing or breathing equipment. During initial radio communications, there was some mispronunciation of the product name, which caused confusion and delay in researching its properties, although it was confirmed as toluene within a few minutes. Thinking that they were dealing with a toxic material rather than a flammable one of the two operators decided to cut a hole in the tank roof to extract his unconscious colleague. He connected his safety harness to the tank's agitator support and worked on top of the tank, as the other operator looked on from the nearby catwalk. But unknown to the operators, flammable toluene vapors were at dangerous levels inside the tank. A hole around the agitator shaft provided a pathway for ignition. Sparks fell into the tank. The ignition of the toluene vapors caused a powerful explosion. The force of the blast blew the top of the tank almost completely off. A flash fire erupted that consumed the flammable gas and quickly burned out. One operator was thrown to the ground and killed instantly from blunt force trauma. In all, 14 operators and contractors were injured in addition to the fatality. An autopsy of the fallen man within the tank indicated that he had died of asphyxiation and inhalation of toluene even before the cutting operation started. This incident emphasizes the need for recognition of all the properties of hazardous materials before the application of appropriate procedures, especially during fire and rescue operations. Whenever you are involved in an accident, do not rush into the scene. Stay calm, take the necessary time to identify the risks and the properties of the hazardous materials that you will be dealing with. This will put you in a better position to handle this kind of situations. This example covers the basic outline of a nitrogen material safety data sheet. Keep in mind, before using any chemical product, please ensure you read the product safety data sheet to ensure you understand the hazards, the personal protection, and first aid measures relevant to the product. Now, depending on printer setup and layouts, your safety data sheet may have more than 11 pages, but should always have information in the 16 sections outlined in this example. Okay, The first section identifies the product and the supplier. In this example, the product is nitrogen in its gaseous state and supplied by Airgas USA. Included here the emergency contact detail. Section 2 lists the hazards associated with the product. This section is useful for safe day-to-day operation. Please use this information to reduce the risk at your workplace. In our example, we can see that nitrogen is supplied as a compressed gas. And like other compressed gases, there are risks related to its pressurized containment when it is stored in high-pressure cylinders. It may explode if heated or if not handled correctly. From the safety data sheet, we can see that nitrogen is not toxic. However, it is considered as an asphyxiant. Nitrogen can actually cause suffocation by replacing the oxygen in a confined space. Thus, nitrogen can be considered as an extremely dangerous gas. And since it is very common in refineries and chemical plants, then you may be exposed to it, so you must always be on your guard. The next section identifies the components in the product and their percentage. As seen here, the product is pure nitrogen. Section 4 covers first aid measures in case of emergency. In the case of nitrogen, the main message is to immediately flush eyes and contaminated skin with plenty of water. And in case of inhalation, the actions to be implemented strongly depend on the situation. For example, if the victim is still conscious, it must be removed to fresh air and kept at rest in a position comfortable for breathing. If the victim is not breathing or if breathing is irregular, an artificial respiration or oxygen must be immediately provided by trained personnel. In all cases, whenever you are involved with a nitrogen incident, never rush into the scene, especially if it is occurring in a confined space. Take the time to carefully assess the hazards and, for your own safety, wear an appropriate mask or self-contained breathing equipment. Also, please make sure that your colleagues and first aid representatives are familiar with these measures. Next, Section 5 covers firefighting measures. Now, although nitrogen in itself is not a flammable gas, you must however use an extinguishing agent suitable for the fire surrounding nitrogen cylinders should this occur. So please check that you have the right type of extinguisher to use in case of fire and review the specific hazards against your use of the product. Keep in mind here, the nitrogen cylinders are under pressure. Thus, in a fire or if heated, a pressure increase will occur and the container may burst or explode. Make sure to isolate the scene by removing all persons from the vicinity of the incident if there is a fire. Section 6 covers spill and cleanup. It is important to go through this section and review in detail how you will deal with a spill and consider what you may need for cleaning up spills. In our example, since the material involved is gaseous nitrogen, the concept of spill and cleanup is clearly not applicable. However, notice what is written on the safety data sheet. Immediately contact emergency personnel using contact detail from Section 1 and stop leak if without risk. Section 7 provides valuable insights into how you store the product. Now, in case of flammable liquids or gases, you should look at ignition sources where these products are stored and handled. In our example, since nitrogen is not flammable and not toxic, the focus here is to avoid direct contact with the product. You can read here, avoid breathing gas, use only with adequate ventilation. Or avoid contact with eyes, skin, and clothing. Or eating, drinking, and smoking should be prohibited in areas where this material is handled, stored, and processed. Okay, next, Section 8 covers exposure control and PPE. Exposure standards are guidelines for controlling exposure. It is important to read the PPE section and review your current practices to ensure that they are in line with the advice. For example, when dealing with nitrogen, it is recommended to use safety eyewear to avoid exposure to gas. Section 9 covers the physical and chemical properties of nitrogen. As seen here, melting point, boiling point, critical temperature, density, and molecular weight are provided. When a property is not applicable or not available, it is mentioned in front of it. For example, lower and upper explosive limits are not available, simply because nitrogen is not a flammable substance. Section 10 deals with stability of the product. It is important to pay attention to this section and make sure that incompatible materials are not stored close to the product. In our case, and as mentioned in the safety data sheet, nitrogen is a pretty stable substance. Under normal conditions of storage and use, hazardous reactions will not occur. However, pay attention to the conditions to avoid. It is important to note here and to keep in mind that nitrogen should not be allowed to accumulate in low or confined spaces, because otherwise nitrogen will displace oxygen and will render the air not fit to breathe. There will be more about this in the confined space entry section. Section 11 covers the toxicity of the product. It lists the health hazards from exposure to the product by exposure routes such as inhalation, ingestion, eye, or skin exposure. After consulting this section of your safety data sheet for a given product, we recommend you review your current usage of the product in question, identify the ways you could be exposed in your workplace, and minimize exposure where possible. Now, in the case of nitrogen, this substance is not toxic, so there is no particular hazard here. Lastly, the next couple of sections are self-explanatory, and we're not going to go through them, so please take the time to review them offline and let us know if you have any question. Lastly, to finish off this video, we encourage you to consult the downloadable resources section. There, we have uploaded a propane safety data sheet. Please review this safety data sheet and let us know the type of hazard that propane poses. Is it toxic? Is it corrosive? Is it flammable? Or perhaps pyrophoric? Please have a look and let us know. Toxicity is the first factor that determines the hazard level of a toxic material. It is a measure of the material's ability to cause adverse health effects to humans. For different materials, the doses needed to produce an adverse health effect vary widely. LD50 and LC50 values are used as a coarse index to compare the acute toxicity of different materials. LD50, or lethal dose 50%, is the dose that kills 50% of a group of test animals. The dose is administered all at once, orally or applied to the skin. It is usually expressed as milligrams of material administered per kilogram of the body weight of the test animal. LC50, or lethal concentration 50%, is the concentration in air or in water that kills 50% of a group of test animals exposed to that concentration for a specified time period, usually 1 or 4 hours. It is usually expressed as ppm, that is, parts per million of material inhaled per kilogram of the body weight of the test animal. Toxicity data for a material is usually obtained by administering the material to mice or rats. Autopsies reveal which of the animal's organs were affected. It is then roughly expected that the same effects will occur in humans who are exposed to the same material for an equivalent concentration and time. The following table illustrates the toxicity classes and provides an example of spectrum of toxic dose. Some toxic substances will be provided next for the purpose of illustration. It is important to note here that only a very small amount of a very toxic material can cause serious adverse effects. The lethal concentrations LC50 discussed in the previous video are all expressed in ppm. Let's take a couple of minutes here and understand what ppm is. ppm stands for parts per million. It is a unit of concentration that is convenient to use when the amount of substance in a solution is very small. ppm is a ratio that compares a number to 1 million and is expressed as follows. The concept of ppm is not much different from percentage. 1% is 1 part out of 100 equal parts, while 1 ppm is 1 part in 1 million equal parts. Therefore, 1% equals to 10,000 ppm. Now, how small is 1 ppm? 1 ppm, or 1 part per million, would be 1 teaspoonful in approximately 25 drams, as seen here. Highly toxic materials require such tiny amounts to seriously affect humans that their limit concentrations are usually given in ppm. For example, the threshold limit value of hydrogen sulfide, a deadly toxic gas, is 10 ppm. That is 10 teaspoonful in 25 drums. Note here that hydrogen sulfide is also flammable, but it is the toxicity that is far more lethal. As seen from the flammability diagram of hydrogen sulfide, the LEL is 4.3%, or expressed in ppm, 43,000 ppm. This is greater than 10 ppm, the threshold limit value of hydrogen sulfide. What this means is that hydrogen sulfide can kill long before its concentration reaches the lower explosive limit. The key message here is, it is important to recognize that some properties of a substance are more significant than others. For hydrogen sulfide, it is the toxicity rather than the flammability. In order for hazardous materials to affect a person's health, it must first contact or enter the body. Hazardous materials can enter our body through inhalation, through breathing, ingestion through eating and drinking, or absorption through skin and eyes. Inhalation is the most common way for hazardous materials to enter the body. Through breathing of contaminated air at the workplace, the hazardous gas, vapor, mist, fume, smoke, or dust enters our nose and our mouth, and subsequently into our lungs. The hazardous materials are then absorbed into the bloodstream and transferred to other organs in our body. These materials can cause damage to specific organs. Some hazardous gases and vapors have distinctive odors. For example, rotten egg smell of hydrogen sulfide, bitter almond smell of hydrogen cyanide, aromatic smell of benzene, pungent urine smell of ammonia, pungent and piercing smell of chlorine, and suffocating odor like musty hay of phosgene. On the other hand, some hazardous gases are odorless and colorless, and they can kill a person instantly without warning. Examples are carbon monoxide, inert atmospheres of nitrogen, and carbon dioxide. Now, having said that, never rely on your nose to detect toxic gases. Some products cannot be smelled before it is too late, while others have no odor. There are also products that inhibit the sense of smell, like hydrogen sulfide. The following 3D animation illustrates the hazards of hydrogen sulfide and emphasizes the fact that you should never rely on your nose to detect toxic gases. It is important to keep in mind here that whenever you work in a toxic or hazardous area, always use a portable personal gas detector and alarm. Install fixed gas detectors and an alarm system in the plant at locations where leaks of hazardous gases are expected. Now, it is best to anticipate the hazards of working with these substances. Always use adequate engineering controls, administrative controls, and wear the appropriate PPE, such as respiratory protection, to avoid inhalation of hazardous gases and dusts. The concept of engineering controls and administrative controls will be discussed in detail further ahead. Some materials, when contacted, can seep through the skin and eyes into the bloodstream. This process is similar to using a medicated plaster to relieve an aching neck. Some gas or liquid materials, such as hydrogen cyanide and benzene and also methanol, can pass through the eyes and mouth, and subsequently enter the bloodstream. Some materials are so corrosive they burn holes in the skin, allowing entry for infection of other materials. Absorption into the body is faster through open wounds, such as cuts and injuries. As a result, all wounds must be treated and dressed promptly. Use a safety shower and eye wash when you come in contact with or are accidentally splashed with hazardous materials. Always use adequate engineering controls, administrative controls, and wear appropriate PPE to minimize exposure to hazardous materials. Avoid skin contact with hazardous materials, solvents, and any products containing solvents by wearing suitable protective clothing when necessary. And remember to report any defective equipment. If work clothing become drenched or saturated with solvents, they will act as a reservoir to bathe the body continually with the harmful materials. So keep in mind to remove and change work clothing or PPE promptly when they become drenched or soaked with harmful materials. In this accident example, an operator collapses after donning contaminated clothing. An operator was opening a bleed valve when he was splashed with wastewater. The wastewater was from the acetone cyanohydrin plant. He later returned to the control room. His colleagues, observing that he was looking unwell, suggested that he have a shower and get some rest. After showering, the operator put on his old contaminated boots and collapsed. He was taken to the local hospital, but the medical staff at the hospital had no knowledge that he had been exposed to acetone cyanohydrin and were not trained to handle patients with exposure to cyanide. The contractor died in hospital. The main lesson here is to never put on soiled or contaminated clothing. Remember, many people have collapsed after wearing contaminated coats, gloves, boots, and so on. Hazardous materials can enter our body through eating and drinking food and beverages contaminated by unwashed hands, gloves, clothing, or are left exposed in the workplace. Nail biting and smoking can also contribute to the ingestion of hazardous materials. Liquid materials may also enter the body through accidental consumption. For example, if a liquid is transferred to a bottle and not labeled adequately, a worker may mistake it for water or beverage. So keep in mind, for your own safety, do not eat or smoke in areas where there are hazardous materials. And after working with hazardous materials, wash thoroughly before eating or smoking. Now, how toxic a material is depends on its toxicity. Its potential to cause harm to workers also depends on the concentration and duration of exposure. There are two types of human exposure to hazardous materials at the workplace. These are acute and chronic exposures. An acute exposure refers to a sudden and short-term exposure. The exposure may last for minutes, hours, or days. It is a one-time exposure to a relatively large amount of a material, usually during an accidental release from operations or maintenance activities, such as improper handling of the materials, runaway reactions, or cleaning of equipment that normally contains materials. The following depiction illustrates a typical example of operators exposed to a toxic chemical. In this example, an accidental release occurred when an operator attempted to manipulate a leaking valve. Note how the toxic gas, which happens to be also highly flammable, quickly spread, formed a vapor cloud, and then quickly ignited, severely burning many operators. A chronic exposure is a repeated exposure over a long period of time, usually to a small quantity of fugitive emissions from flanges, valves, pumps, sampling, loading, and unloading operations. The exposure levels may be too small to cause any immediate health effects. Exposure may last for months or years. Exposure limits are usually given with respect to the period of exposure, taking into account the difference between acute and chronic exposures. The exposure limits available are usually for 8-hour, 30-minute, and 15-minute exposures. Some toxic substances have exposure limits which no person should be exposed to at any time. These limits are known as ceiling limits. Other limits include TWA, TLV, PEL, OEL, STEL, and IDLH. Let's discuss each one of them. Understanding the meaning of these limits will raise your awareness and put you in a better position when in contact with toxic materials. TWA stands for Time Weighted Average Limits. These are maximum concentrations that it is believed most workers may be repeatedly exposed day after day without adverse effects for a conventional 8-hour workday and a 40-hour work week. TLV threshold limit values, PEL permissible exposure limits, and OEL occupational exposure limits are TWA based concentrations. They allow excursions above the given exposure limits, provided that there is a compensating equivalent excursion below the limit during the workday. STEL, or short-term exposure limits, are maximum concentrations that a worker can be exposed to for a period of up to 15 minutes continuously without suffering intolerable irritation, chronic or irreversible tissue change, narcosis of sufficient degree to increase the likelihood of accidents, impair self-rescue, or materially reduce work efficiency. Keep in mind, no more than 4 STEL periods per day are permitted, with at least 60 minutes between exposure periods. Note that the daily TWA limit must not be exceeded. Lastly, IDLH, or immediately dangerous to life or health concentrations, are concentrations from which a worker could escape without injury or without irreversible health effects in the event of respiratory protection equipment failure. Only highly reliable respirators are to be used at concentrations above IDLH. IDLHs are based on the effects that might occur as a consequence of a 30-minute exposure, although in most cases, exit from a hazardous atmosphere could occur in much less than 30 minutes. However, the 30-minute period is a safety margin and is not meant to imply that workers should stay in the work environment any longer than necessary following the failure of respiratory protection equipment. Every effort should be made to exit immediately. Okay, it is important to note here that the choice of type of exposure limit to use depends largely on the conditions and purpose of the activity, such as confined space work, rescue situations, and so on. Shown now on screen for the purpose of illustration, the different exposure limits for benzene. Where the use of hazardous materials cannot be eliminated or substituted, the following measures may be used to control exposure in descending order of priority. First, engineering controls, then administrative controls, also known as collective protection, and finally, PPE. In the next couple of videos, we will discuss each measure in detail. Engineering controls are the most effective method because they remove, isolate, or reduce the source of the hazard, rather than lessen the damage that may result from the hazard. Control must only come after the anticipation and recognition of a hazard. Substitution of a hazardous material or industrial process with a non-hazardous one is the best way to remove a hazard at the source. It totally eliminates exposure to materials that are hazardous. Other engineering controls, such as mechanical ventilation, pneumatic dust transfer, and process enclosure, should be built into the work process. They are less dependent on the chemical user, who, unfortunately, is subject to human errors, such as forgetfulness, preoccupation, or perhaps insufficient knowledge. Some techniques used in engineering controls are substitution of a hazardous material with a less or non-hazardous material, substitution of a hazardous process with an inherently safer process or equipment modification, isolation or total enclosure, ventilation by general or local exhaust ventilation, reduction of process temperatures and pressures, reduction of storage inventory of hazardous raw materials and products, use of equipment that requires less maintenance, use of equipment with no moving part seals, use of secondary containment on mechanical seals. Administrative controls are required either as supplemental hazard controls or to ensure that engineering controls are developed, maintained, properly functioning, and effective. Administrative controls consist of managerial efforts to reduce hazard through planning, information and training, such as hazard communication, safety data sheets, written policies and procedures, for example, the chemical hygiene plan, safe work practices, and environmental and medical surveillance, for example, workplace inspections, equipment preventive maintenance, exposure monitoring, and workers' health monitoring. They primarily address the human element of hazard controls. Other administrative controls include reduction of the number of exposed workers, reduction of the duration or frequency of exposure of workers, good housekeeping, management of change, and lastly, education, training, and evaluation. We hope that we will contribute to the latter and that our training course will raise your awareness so that you will be able to recognize early signs of safety concerns and contribute to the safety of your facility, your fellow workers, and yourself. Gas testing is important when personnel are required to work in areas where exposure to hazardous substances is a possibility. Inadequate or improper gas testing can be a cause of fatal accidents because many people do not understand the basic working principle of flammable gas detectors. Most portable flammable gas detectors operate by the catalytic combustion of a flammable gas on a heated filament, usually platinum, to give a reading of the percentage of LEL. Accordingly, there must be approximately 21% oxygen in the sample to give accurate readings. If the atmosphere being tested is deficient in oxygen, for example, after being purged with nitrogen, it is not possible to use a standard type of flammable gas detector to detect hydrocarbon vapors. Flammable gas detectors must be maintained, calibrated, and operated in accordance with the manufacturer's recommendations in order to give accurate results. Always use the correct instrument for measurement of oxygen, LEL, and percentage of toxics. Do not use gas tube detectors, which change color upon detection, for measurement of percentage LEL. Gas tube detectors are used to determine the presence of low concentrations of a known contaminant, as each tube is designed for a specific contaminant. It is important to note here that some gases may cross-influence detectors, a condition known as cross-sensitivity, resulting in less accurate results. For example, Drager tubes for acetic acid testing results in the same color change, that is yellow, not only for acetic acid but also for sulfur dioxide, leading to inaccurate test results in the presence of this contaminant. So it is important here to always refer to your manufacturer's data to ensure that the right detector is chosen to obtain accurate results. In a similar manner, combustible gas detectors should not be used to measure toxic substances, as they will not measure the very low concentrations of toxic substances present that may pose a health risk. For example, recall the threshold limit value of hydrogen sulfide is 10 ppm. Hydrogen sulfide is also flammable, so the temptation here is to use a combustible gas detector for hydrogen sulfide to measure its toxicity. Now, as discussed in a previous video, hydrogen sulfide can kill long before its concentration reaches the LEL. Fortunately, single detectors are now manufactured to be able to detect a number of gases, for example, oxygen, LEL, hydrogen sulfide, and carbon monoxide. This makes gas testing more convenient without having to carry multiple instruments. However, the background knowledge of gas testing is still fundamental in the interpretation of test results and cannot be overlooked. Now, to put it simply, gas testing must be undertaken in the following order. First, presence of oxygen, then presence of flammable vapors, and lastly, presence of toxics. Keep in mind, if the gas testing equipment is calibrated on one specific flammable mixture, it may be inaccurate for measuring the LEL for another mixture. For example, if calibrated with methane air mixture of 10% LEL, it may give a reading of 29% LEL for toluene air mixture. In addition, a low oxygen reading may mean the presence of a contaminant. This is because when a gaseous substance is introduced, it displaces air, so nitrogen and oxygen, resulting in an oxygen level of less than 20.9%. Now, as seen here, air contains oxygen and nitrogen in the following proportions: 79.1% nitrogen and 20.9% oxygen. This yields a ratio of nitrogen to oxygen of 3.8. This ratio of nitrogen to oxygen in air is always 3.8. As a result, if the reading is 90% oxygen, then the atmosphere contains 8.7% of another contaminant, as explained here. If oxygen is above 20.9%, then what it means is that there is a leak from an oxygen source. In all cases, for your own safety, always make sure all areas of the work are gas tested and visually inspected. And remember, some vapors are heavier than air and tend to settle in low places, particularly in confined spaces. There will be more about this further ahead.
Welcome to the Dregger Accuro Pump and Tube instructional video. I'm Ed Liggis, the U.S. Product Manager for Dregger Tubes. I'm going to show you how to use the Accuro Pump and Dregger Tubes. Prior to using any of the equipment, please read the instruction manual for the Accuro Pump, as well as the instructions inside each package of Dregger Tubes. Check the back of the package to make sure the tubes are within their shelf life. Today I'm using the Water Vapor 1B tube. Before we do anything, we'll need to conduct a leak test on the Accuro. Insert an unopened Dregger tube securely into the inlet and completely compress the bellows. The end of stroke indicator will turn from white to black. The pump is adequately leak-proof if the end of stroke indicator has not turned white within 15 minutes. If the pump leaks, try inserting the tube into the socket more tightly and repeat the test. Otherwise, refer to the maintenance section of the instructions for use. Remove the tube and push the reset button to set the stroke counter back to 0. Take a tube from the package and using the tube opener 7000 included with each pump, remove both tips of the Dregger tube, twist to score the glass, then snap off the tip. The pump itself also has a cutter and tip breaker. Insert the tube into the pump inlet with the arrow pointing toward the pump. Grip the pump and compress the bellows completely. The stroke counter will advance. Release the bellows and air will be pulled through the tube. The stroke indicator turns black when you compress the bellows and pops up white when the pump stroke is complete. Don't start a new stroke until the indicator is white, showing the completion of one pump stroke. Take the required number of strokes according to the instruction sheet in the package. This tube has a high range scale based on n equal 1 stroke and a low range based on n equal 2 strokes. This means that if the discoloration reaches the high range with 1 stroke, read the tube, but if not, take 1 additional stroke and read the low range scale. The discoloration did not reach the high range scale. Therefore, we need 1 additional stroke. Remove the tube and read the discoloration immediately. You can see this reading is about 5.5 milligrams per liter. Using an indelible marker, mark the end of the violet discoloration. The discoloration on the tube may change over time. Compress the pump 4 to 5 times after each test to flush the pump.
When you're in the field and can potentially be in an emergency situation, you need accurate, immediate information. When your detector is in standard operation, you will see the concentration readings displayed simultaneously. Hydrogen sulfide and carbon monoxide are measured in parts per million. Oxygen is measured in percent by volume. Combustible gases and vapors are measured in percentage of the lower explosive limit, represented by percent LEL. Under H2S, CO, and O2 readings, you see the gas type. Percent LEL indicates the presence of combustible gas. In a fresh air environment, you want to see your O2 reading at 20.9% and all other readings at 0. Just like your mobile phone or iPod does, the battery life indicator displays your remaining battery. During standard operation, that is everything you'll see on your screen. Hopefully, you never encounter an alarm. In the event you do, follow your evacuation protocols and your site procedures. How do you know which gas is in an alarm condition? The gas below the reading will flash. In this case, the oxygen sensor is an alarm. In addition to the audible, visual, and vibrating alarm will flash at the top of the screen. The alarm type will also appear. Low alarms are instantaneous alarms. Take appropriate actions in line with your on-site procedures in the event your detector goes into low alarm. High alarms are also an instantaneous alarm. High alarms are a secondary warning level. STEL readings are calculated only for toxic gases. STEL stands for short-term exposure limit, basically measuring your average exposure over a preset time period. This floating window can be set from 5 to 15 minutes. Like STEL, TWA alarms are also calculated for toxic gases. A TWA alarm signals a cumulative exposure over time, typically an 8-hour period. TWA stands for time-weighted average. If you are taking proper action and evacuating anytime a low or high alarm is sounded, your Gas Alert Microclip XL should not go into STEL or TWA alarm. The fifth type of alarm is an OL, or over-limit alarm. This means that the level of gas in the environment is beyond what the sensor can measure. OL will flash in place of the reading of that sensor. Always confirm proper sensor function following an OL alarm. Other easy-to-identify icons and prompts you will see on your screen include Auto Zero, the gas cylinder icon, and Auto Start.